Good morning, good afternoon, and good evening, and welcome to the JavaScript and Friends conference. Now, my name is Håkan Silfvernagel, and I'm going to be talking about WebAssembly and why you should consider WebAssembly for your next front-end project. But let's have a look at the agenda for today. So first off, I'm going to be describing what is WebAssembly, and then after that, we're going to run through a simple Hello Wasp program. Then I will talk about an introduction to Rust, because we will be using Rust as our high-level language that will then compile down to WebAssembly. So in the next section, I'm going to show you how you can write a program in Rust, compile it down to WebAssembly, and then make it into an NPM package that we will upload to NPM. And then after that, we will take this NPM package and use it in our own web application. And after that, we're going to look at a little bit more advanced example of game of life. Then we will talk through performance. And after that, I'm going to be giving you some real-world examples on how WebAssembly has been used. And then we'll go through some future plans for WebAssembly. And then we will go through some other frameworks that are using WebAssembly, and we'll talk about something called new old. And then finally, we have some conclusions and some references. But before we start, I would just like to give you a bit of a background about me. So my background is I've worked with human-machine interfaces for process automation and robotics. And then I've also been a consultant for the past 10 years. My educational background is a Master of Science degree in electrical engineering and a master's degree in behavioral science. I'm also interested in Internet of Things and in artificial intelligence. So I've taken some classes at MIT. I'm quite involved in the local user group community here in Oslo. So I am part of the Norwegian.net user group and also part of the Oslo AI meetup. And I also have a Microsoft MVP in AI. So in our first section, we're just going to be talking about what is WebAssembly and give you a little bit more background of what it is. So it all started out in 2015. There was a group formed by all the major browsers. And then in 2017, they made WebAssembly release. And then in 2018, there was a public draft. So WebAssembly is a web standard, which means that it's supported by all the major browsers, both on the desktop, but also on their mobile versions. So if we compare JavaScript with WebAssembly, we can see that JavaScript is a high-level language. It's flexible and expressive, and it's also dynamically typed. You don't need to compile, and it has a huge ecosystem of package that you can use. On the other hand, WebAssembly is much more low-level assembly-like language. It has a compact binary format, and it promises you a near-native performance. So what happens is that you want to use a high-level language like C or C++ or Rust or Go, and then you can compile these high-level languages down to WebAssembly. So as I said here, WebAssembly is a new browser standard, and parts of the reasons why they managed to get this out quite fast is that it's based on the previous project called asm.js. So if you're interested in that, you can look that up. So WebAssembly is an intermediate language, just in the same way as when you use Java, it compiles down to bytecode, and if you use C#, it will compile down to MSIL code. WebAssembly is a strongly typed language, so it has 4 different types: the 32-bit integer, 64-bit integer, and 32-bit float, and 64-bit float. So now I'm going to show you a quick Hello Wasp program. So actually, as you could see in my previous slide, we don't have any type for characters or for strings. So when you write a Hello Wasp program, you would like to make a simple mathematical operation like addition or subtraction. So that's what we're going to do for our Hello Wasp program. So here we have an example of an ad. So with Wasp, you have a format called WAT, which is WebAssembly text format. So here you can write your Wasp module. So you define your module and you define your function, which we call add2, and you define the input parameters. So in this example, we will take in two 32-bit integers and we will have an output result as a 32-bit integer. So WebAssembly is a stack-based language, so you can pull and pop and push from the stack. So here we add with the get local, we add the first parameter, and we get local, add the second parameter, and then we use a mathematical operation. So in this case, it's the integer 32 add operation. So WebAssembly has support for some 70 different types of operations. And then finally, we need to do an export. So we export with the name of what we want this function to be, or what we want this module to be called. So we want the module to be called add2, and this will refer to the function called add2. So we can use a tool here called what2wasp, and then we can have a look at what it will actually look like in code. So as you can see here in the slide, it looks quite assembly-like in the code. So how do we do now if we want to use this WebAssembly that we have created? So we can create a simple HTML page, and then the first thing that we want to do is we want to fetch this binary wasm file. So we do a fetch on add wasm, and we read it into an array buffer, and then since WebAssembly is a standard, we can just call webassembly.instantiate on this array buffer that we just read in. And then we can assign the result. So we can do results.instant and then exports, and then the name of our WebAssembly module. And we assign that to an object, add2, and then we can just alert out the results of adding two integers out onto the screen. So if we run this HTML file, it will look something like this. So we'll have the result of the addition. Now, another tool that can be interesting to know about is the Wasp Code Explorer. So what you can do with the Wasp Code Explorer is you can take a binary WebAssembly file and then you can upload it into the Wasp Code Explorer, and then you will get the textual representation of that binary file. So in this example, we've uploaded this Wasp file that we just made in the previous slides, and then we can see here that we get the same textual representation as we had before. So now, but as you can see, it will be quite cumbersome to write WASM just as we did in the previous example. So what we really would like to do is we would like to be able to use a high-level language, and then we would like to be able to compile this high-level language down to WebAssembly. So one of these high-level languages that are supported is Rust. So now I'm going to give you a quick introduction to what Rust is. So Rust is a language that comes from Mozilla. It's a system programming language with syntax similar to C or C++. It's a strongly typed language, and it compiles to native code. And one of the design goals when they designed Rust as a language was that it should be memory safe. So that means that you shouldn't have any dangling memory pointers. So in Rust, you need to know about the tool chain. So the Rust tool chain consists of three different parts. It's Rust up, which is the installer for Rust. It's cargo, which is the Rust package manager. So when you're using Rust, you can compile your project and turn it into a package, and then you can upload it to crates.io, which is the package registry for Rust. And then finally, we have Rust compile, which is the compiler for Rust. So here's an example of a Helloworld program. So what you do is you define a main function, and then you define here that we want to print out Hello World in that function. And then you can just use Rust compile on your main Rust file, And then on a Windows system, it will create an exe file. And if you run that exe file, it will print out hello world on the command prompt. But you can also use cargo. So you can use cargo new hello world. So this will create a new project structure. And then you will have a main Rust file where you can define what you want it to do. So you want to print out the hello world, and then you will also have a TOML file. So this TOML file is a package description of your package. So in this TOML file, you need to define what is the name of your package, what is the version, and who are the authors, and also if you have a dependency on any other package. And then you can run the cargo run. So what will happen then is it will compile your your project, and then it will generate an exe file and run that exe file. So you can see here that the result of this is that you will have hello world out on the command prompt. So in Rust, we have a number of different types. We have both primitive types and primitive constructs. So some of the primitive types is integer and float, and we also have char and strings, and we have primitive constructs such as arrays and function pointers and references. So now when we know a little bit more about Rust, I'm going to go through an example here of how we can write a program in Rust, and then we will compile this program down to Webassembly, and then we will upload Webassembly to NPM, and then finally we will use this NPM package in our own web application. So the first thing that we need to do is we need to be able to compile our Rust programs to Wasp. So first step is to install this Rust toolchain that I was just talking about. And then after that, we need to add the compile target. So in this case, we need to add the wasp32 unknown target in order to be able for us to compile a Rust program down to WebAssembly. And then finally, we need to install something called the Wasp bindgen. So the Wasp bindgen is a package that will generate bindings to and from JavaScript to our WebAssembly. So you can call the Wasp bindgen for a glue script. So this is the glue between your application and your WebAssembly. So here's an example of a Rust example here. So first we have the package definition. Just as before, we have the name, we have the version, and we also need to define some libraries that we're going to be using. So in this case, this library is called C dynamic library, and we also define a dependency. So in this case, it has a dependency on Wasp bindgen that I was just talking about. And then we have our main Rust file. So in this Rust file, we define that we want to be able to use an external crate. In this case, it's the Wasp bindgen, and then we can mark up our function where we want to be able to use this Wasp bindgen. And then we define that we want to be able to use an external JavaScript function. So in this case, it's the alert function. And then we define the function that we will be able to call from our calling application or public function. So in this case, it's the function called greet, which takes a string as an input parameter. And then we are using the standard alert function to alert it out onto the console. So now when we have our program, then we can use wasp pack init in order to package this into a folder called pkg. And then we can just use the regular npm publish in order to publish this as a package up to npm. So if we look into the pkg folder, we can see that there are 4 different files. So we will have a look into the content of these files in our next slide. But if we run this npm publish package, then what will happen is that then this package will be published up to npm. So we can see here that our package is on npm called Hello Wasp Silver, And then in our next step, we will actually be able to use this npm package. But before we do that, we're just going to have a quick look into the content of these 4 different files. So the first file is a Typescript file where we actually are defining the functions that are defined in our WebAssembly. So in this function, it's a function called greet, which takes a string as an input parameter. Then after that, we have something, the helloWaspSilver.js. So that is this glue file that I was talking about. So we can see, for example, here in the greet function, it tries to pass a string down to wasm, and then it returns wasp.greet with this thing that we were passing into the function. And then finally, we have our package definition, which is a regular package.json file. So if we want to be able to use this package, then we can create a webpack config file where we just define our entry point, which is index.js. And then we also define a standard package JSON file where we say that we have a dependency on this hello wasp silver npm package. And then we define an index.html file where we want to be able to bootstrap our application through an index.js file. So in this index.js file, we're actually importing this package, the hello wasp silver package. And then we need to load this asynchronously. So when we do that, we can call JS. So we assign this to an object, and then we can call js.greet, and then with the text that we want to have printed out. So if we do that, we can see here that then we will get the hello world example that we defined. So now I'm going to continue with a little bit more involved example called the game of life. So first, I'm going to go through the rules for this game of life application. So the rules of the game of life is that you have a simulation which takes place on a board and with some different cells. And then there are some rules that if you have any live cells with fewer than 2 live neighbors, it will die as if caused by underpopulation. If you have any live cell with 2 or 3 live neighbors, it will live on to the next generation of the simulation. And if you have a live cell with more than 3 live neighbors, it will die because of overpopulation. And then finally, if you have any dead cell with exactly 3 live neighbors, it will become a live cell through reproduction. So if we run this example, it will look something like this. So you can see here that we also have included a pause button, so we can pause our simulation, which we'll do here. So now we can go manually into the simulation and add some new cells, and then we can continue our simulation. So now we're going to have a look at how this has been implemented. So the first thing that we have is a TOML file. Again, here we have the name of our package, and we define what type of library, what type of crate this is. And then we also define our dependencies. So as before, we need to have this wasp bindgen in order to generate this glue file. And then we have our main Rust file. So in this file, we define the board for our simulation, which is called the universe here. And we also define some getters and setters in order to get the width and height of our simulation board. And we also define a function here called toggle cell, where we enter the row and column for the cell that we want to be able to toggle. And then we also have this Typescript file where we define the different types of functions that a calling application can use. So in this case, we can call the width and height, and we can call cells to get the number of cells, and we can also call, for example, the toggle cell function. And then this is, again, this glue file that I was talking about. So for example, in the toggle cell glue file, it tries to call down to wasm, so it tries to return wasp.universe and then toggle cell function. So if we want to be able to use this, we can define an index.html file, and in this file we define a bootstrap.js file where we are loading this index. So here in the index.js file we define our universe, and then I've just marked here in red that we can call down to the universe.toggle cell with the row and the column index. Now I'm going to go through a little bit more about performance of WebAssembly applications. So as I said, initially what the WebAssembly tries to achieve is they want to have near native performance with WebAssembly. So here is an example here of where we have run the same calculations both with JavaScript and WebAssembly and in 3 different browsers. So what we can see from this image here is that that on the whole you can see that WebAssembly is a lot faster than what JavaScript is. But maybe what is even more interesting here is that you can see that with JavaScript you have a quite high standard deviation of how much time this operation will take. So for example, in Firefox, you can see it has the largest spread, whereas in WebAssembly, you have a very low standard deviation, which means that you will be able to calculate the performance of your WebAssembly applications and rely on that performance to a much larger extent than with a regular JavaScript application. And we should also take into account that JavaScript has been around for quite a lot of time and the JavaScript engine has been optimized, whereas WebAssembly is a lot newer. So with time, we can envision that this performance difference will actually be even larger than what it is today. So now I would like to give you some examples on how JavaScript has been used in the real world. So the first example is the DSP library, a digital signal processing library. So I should also say that this is actually one of the best types of use cases where you actually have an application, maybe written in C or C++, that you want to be able to expose on the internet. So what you can do then is you can compile down your application to WebAssembly, and then you can just use the WebAssembly in order to make a web application out of that library. So that is what these people have done. So they had an existing digital signal processing library written in C, and then they compile it to WebAssembly. And this is what it looks like. So you can see here that you can use different types of filters in real time, both on a video or on an image. And and you can see the results from here. So the important thing to take away here is that you didn't have to change anything in sort of your application logic. So you can just create a layer on top of that using WebAssembly, and then you can embed it into a web application. Another example is Autocad. So Autocad has a lot of different drawings. So what they would like to be able to do is they would like to be able to expose these drawings to their customers using the browser. So in 2018, they launched something called the Autocad web app, which is using WebAssembly. I'm going to just give you a quick overlook of how the architecture is for this application. So on the bottom, you can see that they are using, so the Autocad is written in C++, so they can still use their C++ libraries from before. And then they are just using a WebAssembly layer here in order to be able to communicate between the C++ code and the front-end code. So the front-end code they are free to use whichever framework they would like to use. So in this case, they have settled for React and TypeScript, and then this calls down to the WebAssembly, which in turn calls the C++ code. And this is also a good example of separation of concern. So what you have here is that you can have your front-end developers can focus on the React and TypeScript, whereas there are C++ developers which can focus on the existing Autocad core functionality. So now I'm going to go through some future plans for WebAssembly. So what is next here? So one thing that I think you've seen here is that we've needed to load our WebAssemblies using an asynchronously call. So what I would like to be able to do is that we should be able to call directly to the DOM or to an web API. So that's one thing that you can't really do as of now. And the second thing that I would like to be able to do is to directly import Wasp into JavaScript just using a regular import statement. And the third thing that I would like to be able to do is to support more languages. So as I said here, they're supporting C and C++ and Rust and Go, but they don't support out of the box any managed language like Java or C#. But that's something that they're looking into. And another thing which can be interesting here is something called Serverless Web Assembly. So WebAssembly is not only for the browser. There are some providers like Cloudflare and Fastly. They support WebAssembly. So what you can do is you can write your logic as a serverless function, and if you do this using WebAssembly, you can reach fast launch times, and it's also you can use, as we said before here, if you already have some libraries, you don't need to rewrite them to JavaScript. Instead, you can just use WebAssembly instead. And an example of how this can look like is on this picture here. So either you can have a front-end application which calls a back-end application where you have the data processing in the back-end application. Or a second alternative is that you're doing everything client-side. So you have the main front-end, which is calling a JavaScript library on the front-end, which also does the data processing. Or you can have client-side WebAssembly, where we have the main front-end logic, and then you have the data processing, which is in the form of the WebAssembly. Or you can use the serverless WebAssembly. So here you have the main front-end logic, and then you have on in the cloud, you're running a serverless application where you're using WebAssembly for the data processing. And another thing that I would like to talk about is something called the WebAssembly system interface. So there are plans here in order to make WebAssembly running outside of the browser. So you can see WebAssembly as a language for sort of a conceptual machine. So so when you are trying to call OS functions, you need to use something called system calls in order to be able to call directly down to the OS. So this is an example of a proposal of how this could be done. So this is from a blog post by Lynn Clark. So you can see the link here on the slide, and you will also see it in my reference list. But basically what it is that you have a separate layer that can negotiate between the operating system and the WebAssembly in order to give the WebAssembly component rights in order to call down to the file system or call operating system functionality. So now I'm going to go through some other frameworks that are also using WebAssembly. So one of them is Pyodide. So Pyodide is a framework that brings the Python runtime to the browser using WebAssembly. So this means that you can do scientific computations with Python libraries inside your browser. So the way that this works is they have a version of Python called CPython that they have been able to compile this runtime down to WebAssembly using a compiler called mscripten. So that means that you can run your Python runtime in the browser, and then you can load your regular Python libraries like NumPy, Pandas, Matplotlib, and SciPy, and so on in the browser. So, for example, in this example here, we are in the browser here, we are generating some test data, and then we're using Matplotlib to plot, in this case, a sinus curve. So this is one way that you can use WebAssembly. So another one of these frameworks is called Assemblyscript. So with Assemblyscript, you can compile something, you can compile a subset of Typescript down to WebAssembly using a compiler called Binarin. And so this is an example of how this looks like. We call a rotate function, where we have some input height and width, and also a rotate parameter. And one of the important things to take into consideration here is that you need to be able to, you need to handle the memory allocation yourself. So, for example, we can see here that we define a pointer object by doing memory.allocate. Then we need to do something with the pointer, and then we need to make sure that we free up this memory. So we do memory.free on this pointer. So another thing which is also important to keep in mind is that this is a small project. It has, a couple of sponsors, but it's nothing like, for example, Mozilla or anything else. Another example is Blazor. So Blazor is a Microsoft framework. So with the idea here is that you should be able to build a whole client web application just using C#. So that the way that they can do this is that they have a version of the .NET framework, which is called Mono, that you can compile down to WebAssembly. So basically, you will have the .NET framework running in your browser using WebAssembly. So you have a couple of different ways that you can run Blazor. Either you can run it on the server, and then you can have events that are sent back and forth using SignalR, or you can run it on WebAssembly, and then you have the .NET framework running in your browser using WebAssembly. Now we have a section called New Old. So the question is, haven't we seen all of this before? So if we go back in time, we had other components that had similar promises as WebAssembly. So we had ActiveX, and we have had Flash, and we also had Silverlight. But one thing that distinguishes WebAssembly from these previous components is that WebAssembly is a web standard, whereas these previous attempts, they have all been proprietary alternatives. So now I think that we have a much higher probability of having WebAssembly succeed than what we had with these previous 3 examples here, because of the fact that it is a web standard and that all the major web browsers are supporting it. So what are the conclusions here? Should we go WebAssembly all the things? When I started out with this and looking into WebAssembly, there were lots of blog posts that JavaScript is dead and WebAssembly should take over the whole world. But that's not really the case here, I think. I think that WebAssembly is just another tool in your tool belt, which can be great. For example, if you have an existing library that you would like to be able to use on the internet, then you can compile this library to WebAssembly, and then you can just expose it using WebAssembly. So that's a great use case. But as of now, so it's quite difficult to actually do some changes to the DOM and things. So we'll see how it evolves here. But I think that there is no need to worry about being a JavaScript developer. There will still be a lot of things to do. And then finally, I have some references. So you can look through these web references in order to learn more about WebAssembly, or in order to learn more about Blazor, for example. So with that, would like to thank everyone for your attention, and I wish you a great conference. And if you want to reach me, you can reach me either on Twitter or on email. Thank you so much for your time.